Hey, welcome to another coding session. I do feel like maybe we got a little bit off track recently. We've forgotten the goal, which is to get to the GPU, right? We want to get some parallel code, we want to get to the GPU. Got a bit carried away with just like things that I found interesting in the language. But I want to focus in on some milestones that I feel like are going to help us reach the goal. One of those things that I had on the list was calling C. And I thought like a nice little simple test we can try to get that working is GLFW. It's always nice to have something visual, right? We can see if we can get a GLFW window opening, and then in future episodes or future videos we can move towards, like rendering something on there with OpenGL, and as part of the part of each frame we can start doing some parallel code and work from there. That's kind of the idea I have. I think that's kind of a little more interesting maybe than just, the programs we've had so far just output various, return codes. That's like all they do. Maybe they print out a little bit of text. Not very interesting. So let's work towards something more interesting while also working towards the goal. That's what I have in mind. Okay, so without further adu, let's have a look at I've got the GLFW reference open here. GLFW, if you're not familiar with it, it's like a cross-platform windowing API, which is great for, if I go to the introduction, if we go to like the home page. See, it says here, that's an open source multi-platform library for OpenGL, OpenGL-ES, and Vulkan development. So it provides you like with a window, and I'm going to probably use OpenGL, so it provides you with an OpenGL context. So it does a lot of the heavy lifting so that you can go ahead and write some OpenGL code. And all we want to do today is call two procedures. This is GLFW is written in C. So because I wanted something where we call C. Ultimately, when we go to the GPU, the way that I'm thinking to do that is via OpenCL. So the user of my language will not have to use OpenCL directly, but under the hood, it's going to call OpenCL, which is also a C library, to interact with the GPU. Because that's also a quite cross-platform library. So for GLFW, the first thing we want to call is this procedure here, GLFW init. It's quite simple. It doesn't take any parameters, and it returns an int. Technically, ints in C, the size is platform dependent. Most commonly, it's 32-bit, but it might not always be. We're just going to assume 32-bit for now because I don't want to deal with that. So let's see. I'm just going to remove all of the playground code that we had, and let's just start doing something more interesting. So GLFW init. How do we call C from Bangalang? That's the question. Well, first things first, we need to define this procedure. Ultimately, I would want to be able to do something like this. Like GLFW is a proc that returns an I32, just like this, and then maybe have something like this to declare it as an external procedure. Maybe we'll get to this. Maybe we can do this at the end of the episode or the video. I don't want to say episode anymore. It feels too old school. But right now, instead of having this declaration here, I'm just going to hard code it. So at the moment we have, where are they? here we have print and exit, which are like syscalls, and we just hard code them in here. So I'm just going to add GLFW init to the list. And it has a return data type, which is, so it's a C int, but I'm just going to call it an I32, and it doesn't have any parameters, so that's it there. Just has a return type and procedure. And then we add it to the procedures. Now there's one extra thing we're going to have to add here, because we don't define this anywhere. You know, these two here in generation, we have defined them, right? We hard-coded them, the assembly here. Whereas this is an external procedure, you know, which is why I thought to have something like this. So I think what I want to do is have like a directive or something. Let's see if this makes sense in the long run. Maybe we'll change it, but basically I want to add some metadata to this procedure to say this is defined externally. So let's just add that to the struct. Okay, so now we've defined our procedure, which means that this should pass type checking. But if we try to run that, I'm pretty sure we're going to have issues. Yeah, so in the assembly, GLFW init is not defined. So the other thing, because here we defined these, so we need to also define the other one. And the way you do an external one is you do extern GLFW init. That's how you define a procedure which is not in this binary, but in some other binary. Or there's probably, some other technical term for a translation unit or something. I don't know that stuff so well. So anyway, we're not defining it, someone else is defining it, so it's extern. Which is why I chose extern as the directive, because it kind of makes sense. So now it's defined, but if actually this is something that I've noticed. Maybe we'll clean this up. See all these strings are defined here? These are test strings, but they're an example. See in test, you'll also find them down here, same ones, but they've been carried across into here, which I don't like. And the reason for it is because we just defined it as some global. So I think I'm going to put it like here. Data section strings. Okay, and this is reminding me of actually an issue that I think we need to resolve, a separate issue. But for now, let's just do this and this. Okay, what's this error? Ah, that does not need to have on there. So that should be happy. The issue that I realized, if we go down to 4, there was this generate declaration. And in the last video, what we did, if we show history, we look at the last commit, we can see that there was this comment here, which was also in type checking, and I thought, oh, we must have just copy pasted this here, and it's not really necessary. But it is necessary because we do this declaration which performs an allocation. and we never clean it up. We never clean it up until the end of the procedure, but I think we should clean it up now, or I guess, you know, this context, whenever this context finishes, we need to clean it up, but we don't. Well, I guess we do, but we want to do it earlier, because say this context is scoped to a procedure, and then we have just like a whole bunch of for loops. Every for loop is going to contribute to the stack, you know, just like put bloat in the stack. I think that's not very nice. So, sorry, this is a bit of a side quest, but I just want to tidy this up. I think this is an issue. So we're going to copy the gen context like so, and then everywhere in here, I want to use the for context. Basically anywhere where we see context, change it to for context. Oops. Like so. And then what I want to do, because we have a few places where we create a context like this, you know. So I think, sorry, I'm scrolling around a bit here. So scope here is another example. So we make a copy of the context. And then we have stuff like this and like this, which is basically like cleanup. It's like, okay, we're finished with the context. Now we need to do something. And I think we need to extract that, because I think it's a bit error prone the way we're doing it right now. So here's copy gen context. So let's say close gen context. And actually I want to pass in two contexts here. One is the okay, so let's say this is the this one's the parent context. No, this one. Sorry, I'm all over the place. Okay, we pass them in as pointers, and then this is where we want to do like this kind of thing. You know, whatever information we need to whatever information that was updated while we were in here and we want to take back to the parent context, we need to make sure that happens. So one thing that we need to add to that is, I'm not sure why I scrolled down there, but no, actually it's here. So data sizes doesn't change in proc. Stack size, variables we don't want to take back up. But there is this new one that we put in here, right? This data section strings is something we want to maintain. If a child scope adds some strings, we want that to propagate back. So we go like that. And then the other thing we want to do, go back to our scope, is this here. So we want to just make sure say close context. I guess we need to pass the file in. I feel like we don't really need to, like, we're never really going to use this context after. but let's do this anyway. Yeah, so we close the context, because this is the reason we pass the context in here is so that when we do the deallocation, it reduces the stack size, which doesn't really matter because we're never going to use this context after, generally. Okay, so there's probably a few places where we do something like this. Here, so when we see this is the same pattern, right? When we finish a procedure. So I want to do, was it close gen context, file, like that. Probably need to point it to that. Maybe I'll add this in here so we don't lose that kind of information. It's kind of the name, I guess, of the context. Okay. So that's that. Then we come down here and we have the scope. So when we close the scope, we put the scope context in here, and that takes care of that and that. And then we have another one here where we close an expression. So see, this is where, like, in this case, we're not, well, I guess an expression cannot contain ifs or fors, so we didn't really need to maintain those, but it can contain strings. So now it is necessary that we do something like this. So close gen context. Like so. Probably need a pointer to this. And expression. Right? Close expression, yeah. Okay. So yeah, I feel a bit better about that. Sorry, that was a bit of a detour. So now if we run that, we get all sorts of issues. So actually, this here, we should only update the parent to be the same as this if it's inline. Maybe I'll put that on the end. So if inline, do these. So an expression is inline, yes. So we can see that was inline here. Yeah, we kind of need to just match those. So this one was inline. So make that one inline. This one I believe was not. It was not inline. So we shouldn't need to do that. I have a feeling it's still going to have the same errors. So that's a bit annoying. We went on a side quest and then we caused all sorts of issues. So this is tests. So we have like F2, F3, F4, F5, 6, 7, 8, 9. Then we have 4, 0, 4, 0, 4, 0. Feels like the 4 is just not getting, did I? Maybe it's because we were playing with the for loop just now. That's right. we're playing with the for loop just now, and we also need to, because we moved this into here, so we need to close this one now. We hadn't done that yet. So it's inline. Okay. It's not happy with that because it's the 4. And now we have string 0 not defined. So now we're not getting any strings. So we're doing a good job of breaking everything. So the data section strings is always getting pushed back up. But we don't, it's getting pushed up, but it's not getting pulled down. That's it. Failed test segmentation fault. That's not very nice. This looks like the issue we had before, right? Yeah, we had that issue and we resolved it, and now we seem to have reintroduced it. So we kind of need to do this. Kind of need to do 2 of them. No, that's still not happy. Do we still have that same? We do still have that same issue. So we're closing that. This one should not be inline, actually. I don't know if that's going to cause an issue. We put false. So we still get this here. So we're still, this close is kind of special, I think, actually, because we don't want to do this. So what's happening here? So when we generate the procedure, we're doing these kind of allocations. They're not really allocations. We're not actually allocating. We're just saying, hey, this will, in the context of this procedure, this is going to exist on the stack. This is going to exist on the stack. We're not allocating them here. We're just saying, hey, these exist. And when we're done, so we don't need to clean them up here because we're not allocating them here. So I think what I'm going to do is just say, hey, the stack size is actually this stack size. You know, there's nothing, we don't need to do, that's basically saying we don't need to clean up. I'm just going to reset the stack size to how it was when we first came in here. Okay, undefined reference to GLFW init. This is failed to link. That sounds like a more reasonable error. Now that we just went like on a massive detour there. Hopefully, so now we don't have all these strings, so that's nice. We have a pointless section data, but we also have this. So because we have this, it assembled correctly, but now it failed to link because we don't have this anywhere, right? This is in the GLFW binary library, and we don't link to that. So here's our linker command. So what we're going to need to do, this is a bit janky. Like, really, we should have a way of passing these things in. So I'll just put a comment, but I'm just going to put a -L GLFW. So that's just saying link with GLFW, please. I think we're still going to get an error. And this is, I did a bit of research, a bit of playing around, and I found this here is what we need. It's saying that we want to link dynamically, and this is the dynamic link we want to use. Now this, hard coding this here is obviously like super not portable and very specific to my setup probably. But I tried it before and it works. So yeah, this and this, it's not great that we're doing it like this, but I'm pretty sure this will work now. Ah, we get a segmentation fault. Okay. And why is that? Allocate, deallocate, copy that onto the stack. Well, that doesn't seem right, does it? Because oh no, it's copying the stack pointer, but not using it. Oh, okay. Yeah, so I think that's fine. It's just not really doing anything actually, and then it's just exiting. So all we're doing is calling GLFW init, but it seems not happy with that. Let me just have a look at my notes, because I did manage to get this to work before. It took a bit of work. So I've hard-coded them. 64-bit calling convention doesn't matter actually yet because we're not passing any parameters. We kind of are doing like the return. That's what all this business is about, the return. But I don't see the harm in it. So I'm a bit gutted actually that this is not working. I thought because I'd done the checking before that this would work. Shell GLFW. And because we just get this segmentation fault, it's super not useful. So let me just do some checking around here. I just want to check whether this is actually causing issues, the fact that we're doing this, all this business. So let's take this out and let's take this out. This is all the handling of the parameters and stuff. We'll take out the deallocation. So we're just doing call and procedure. Process finished with exit code 13. Well, I'm a little bit confused actually, because this doesn't seem to have changed. We still have all this stuff, which I was sure was to do with the this call here. But maybe it's actually to do with, no, yeah, what else could it be? I mean, this also, so this is where we do the, this is this one. So I would expect this one to still be here, but. Oh, and actually this would cause issues. This would cause issues because one of the things that I found out when I was learning about this, calling C, is that the stack needs to be 16-byte aligned whenever you do a call. So when we subtract 4 from the stack, it should be 16-byte aligned at the beginning. But now that we've done the sub 4, it's not anymore. So I'm a little bit confused why it's still doing that. So we do generate call. We should be doing this generate call here, right? Right off the bat. Oh, it says failed tests. Wait a minute, failed tests. It says failed tests, but it hasn't printed anything else out to say that the test has failed. What happens if I just skip running the tests? Okay, so the main program, yeah, now I've removed that stuff. The main program works. I don't know why the tests are not working. But see, if I put this stuff back, I think it's going to crash. Yeah. And that's because it's not aligned correctly. And actually, this is where we need to make a big change anyway. So we want to say if we want to check this extern thing again. And if it's extern, then we need to do the procedure call differently, because currently in here, we're using our own calling convention that we just invented ourselves. But if we're doing an extern one, then we need to use the C calling convention. We're on 64-bit Linux, so it's like, I've looked this up, here it is. Yeah, it uses this System V AMD 64 ABI. That's the name of the calling convention we need to use. It doesn't matter too much right now because we're not passing anything in. We are returning something, and by this convention, the return value goes into racks, or XMM0 if it's a float, but we're not going to handle that right now. So I think what we're going to do is we're just going to say, hey, the return value is in a register. It's the AX register, and the size is the return byte size. Right? Then I can just put that in here. So that should handle the return value. And nodes do not actually have directives yet. But I want to add that here as well because we need to get it from type checking to generation. Type checking has these procedure objects, but they don't get passed through to generation. So when we do a call, I think as part of the call, see, we get the procedure object. And here I want to go node.directive equals procedure.directive. So now the node has that directive information, and we can use it here. So then we should just print out this simple, why are you complaining? It does have a directive field. Oh, of course, yeah. Since we added something to the object, and I think we added it here. There we go. Exit code 0. Yeah, we never actually use the return value. So although here we're reporting that this is where the return value is, but we never use it, so there's no assembly that's needed. So now it's just incredibly simple, right? Like call GLFW init. Okay, that was a bit more of a mission than I expected it to be. I'm a bit curious if we somehow solved this, but okay, all right, good. We're all gravy. I have no idea what was causing that issue before, but it's gone. So now we need to move on. Now that we've got one C procedure working, happy, we need to move on to the next one. Go to the window reference here, and we want GLFW create window. So it takes in a width and a height and a title, which is a char star. So this is a C string. We'll get to that in a minute. And it takes these other 2 pointers. I'm not gonna try and make this GLFW window thing or monitor. But what I'm going to do is if we define this procedure alongside here, so what does it return? It returns this pointer. I'm just going to say it's a pointer to an I8, whatever. It's just a pointer. I don't really care what it's like, what I tell it that it's pointing to. And these are all the parameters. And likewise, I'm going to say that these last 2 are just pointers to I8s. So that's these. I'm only going to pass in null pointers anyway. So it's just a 0, right? So who cares? This one is going to be a C string. We need to create a C string type. And these 2 are ints, right? We said before that ints in C have variable size depending on the platform, but we're just going to say I32. So this is our create window procedure. In generation, we're going to need to have this defined like so. All right. But now to call it, we're going to need to have a C string. That's going to be the tricky part, and these pointers. So yeah, both of those things present some problems. Let's see if we can, why not? Let's postulate what this would look like. So this is returning a pointer to an I8. This is like the monitor, I think it was. What did they call these? Monitor share. Width I32, height I32, oh, I31. And then title is a C string. Yeah, so that's what it would look like if we were to define it. And then if we're going to call it, we would need, like let's say 1920 by 1080. And let's say Bangalang is the title. And here we need, some null pointers. So I'm just going to say a pointer to an I8. I'm just going to declare one to use as a null pointer. So this here is uninitialized, right? I'm just saying, hey, I'm declaring this, but I'm not assigning anything to it, so it's uninitialized. It would be good if we had something like this maybe, to explicitly say, hey, set it to 0. We don't have that yet. But one other thing that I was thinking would be nice to add to the language is 0 initialization. So if you do something like this, you're implicitly saying, hey, just initialize it to 0. i.e. a null pointer. I asked Grok about this, setting memory, and he told me this is how you do it. So let's have a look at that. And where we want to do it is in our generation of a declaration. We're declaring, here we go. So we're declaring this, where are we? We're declaring this variable, right? So we have a look at the declaration, and this is where we go if we are assigning something to it, right? Left-hand side node is the first one, and this is the right-hand side node. But in this case, we don't have a right-hand side node. So this is where we would zero initialize by default. So let's do that. Oops. I think I can remember what these are. So if you remember from a previous video where we did copying, here's our copy code. So it's very similar. This is copying from a source to a destination, and we provide a count. So we know how many bytes we want to copy from the source to the destination, and then we do this repeat move SB, which is basically like repeat copying the byte from one to the other. And also it moves along the buffers as it goes. So here we have repeat, I guess it's store. And Rax is, I'm just going to do, I know XOR is supposed to be better, but I'm going to do this. And we're zeroing here. 0, and this is the destination, and this is the count. And the one thing we need to change here is this is Q for quad word. We want to do byte. Quad word might be more efficient in some cases, but just to keep things simple, I'm going to say byte. So we say, okay, let's go from here. No, this is where we want to set the 0 bytes. This is how many bytes we want to set. This is the value we want to set on those bytes. Now do it. That's basically it. So the amount of bytes is the data size, right? Which I think I've used the convention of calling it a byte size now. So let's call it a byte. Oh, that goes there. %i and %s, the source, which I think we'll do a layer. That's what we did in the copy as well. And we cop like the top of the stack is where we've just allocated, right? So that's where we want to set the bytes. So that should zero initialize with a bit of luck. That should zero initialize this to make sure that we're passing null pointers here. And this is just integers, no big deal. This one here is what we need to take care of now. I think I'm just going to do this. If there's a C, then that's a C string. So we're actually going to have to change some tokenization now. And I guess it's actually a grammar change. You know, there's a string and a C string. Okay. So let's add that to the grammar. String C string. And then we'll define it as same as a string, but with a C in front of it. Okay, that bracket. Oh, that bracket should not be on either of those. I don't know what that bracket's doing there. So let's cut that out. There. That's better. Actually, I'm even going to go further and say it needs to be like, they need to be together. It's just like, it's kind of like one token. C double quote. Okay. So then in tokenization, let's add a data type here for C string. And where's our string handling here? So in this case, we're going to peek 2 runes and look for this. Well, that was nice. Look for that combination. And if we find it, we need to skip past the first rune, which is the C, and then we need to read a string. And then we need to create a C string token. Okay, so that's tokenization. We should get a C string token. So then in parsing, we need to be able to handle that. Where's all our cases? Here we go. So as well as string, there's C string. Basically, we just map. Yeah, a lot of these we just map, but now we need the token type. Okay, no, the node type we need. String, so let's add C string there. Cool. Type checking, I don't think we need to change anything in type checking. Yeah, I think it's fine actually. But generation, we need to handle, well, actually, type checking, yeah, we do need to handle this. So if it's a C string, we give it the type of C string. Okay, yeah, that was one thing we needed to do. And then generation, when we're doing the primary, we also come across, here's the string. So C string is going to be quite similar, but we allocate, we'll need to provide a data size too. But, okay, so I should probably say what a C string is. Maybe that's helpful. Here's a string in our language. A C string is just a pointer, basically. That's it. But the way that but then how do you know how long it is? And the way that's done is you have a null terminator. It's called a null terminated string. So you have all of your characters, and then you have a 0 at the end. So then when something is doing something with your string, it'll like process each character, and then when it gets to the 0, it'll say, okay, we're done. That's finished. That's the end. That's how it knows. In our string, we've explicitly added a length. That's kind of how some newer languages do it, but this is how C does it. And because we're passing the string to C, we need to do it the same way. So we need to use the data section. We need to make a C strings list. And this here, yeah, this here is getting the length. So this was putting the length into the newly allocated stuff. We don't want that. Instead, we want just this, which is putting it's the pointer to the string, or the C string. And I think this is so it's at the top of the stack now. Previously, like for a regular string, the length is at the top of the stack, and the pointer was 8 bytes back. But since we only have the pointer now, it's at the top of the stack after the allocation. Great, I think that's it. So now we need to handle these C strings. So this copy business, we need to handle it in there. That's the close, and here we need to handle it. And then it needs to actually exist. Oh, before I go too far, we need a C string is 8 bytes. Just to be a bit more explicit, it's the address size. That's a pointer, right? It's a pointer. So yeah, this needs to have C strings in it now. That should get rid of all of our errors. And then we need to actually output the C strings. So this will be C string, and we'll just call it C string. And the difference is going to be, because we didn't trim off the quotes or the C at the start, we need to trim off the C now, so that this will just be the string in quotes. And then if I do (0), that's going to add the null terminator at the end. So that's how we store our C string in the binary, in the executable. Is that it? Not happy. Not happy. So we don't have a C string in here. That could be one issue. So this is our declaration of our pointer. 8 bytes. Which has misaligned this. We probably need some way of making sure that things are aligned before we do a procedure call. I think I remember Grok told me how to do this. In x86-64 NASM. It gave me yeah, you can do this. This is what it told me to do before. Rounds RSP down to the nearest 16-byte boundary. Yeah, so it could potentially allocate a bit of space that's not needed, or that we're not using, but it provides the alignment. Don't ask me how that works, but apparently it does. And let's just put that, generate procedure. Isn't it generate procedure? No, generate call. It's the procedure call. Where is the call? Here we go. Here we go. So before we do this extern, call, let's just add this to align the stack. We probably could omit it if the stack is already aligned. So maybe we can say context, if context stack size mod 16 does not equal 0. This will tell us if the stack size is a multiple of 16. And if it is, then we don't need to do this alignment. That's a waste. Let's see what happens now. Okay, width greater than or equals 0 is failed. And that makes sense because in here, we're not doing anything to pass the parameters yet, right? We're just calling it. Like, you don't see the size, you don't see the 1920 by 1080 anywhere. We're not passing any parameters. To know how to do that, we've got this calling C convention here. We've done the return type, but to prepare the arguments, if we're just doing integers and pointers, which we are doing, these are the first 6 registers, or these are the registers for the first 6 arguments, and then after that they get passed on the stack. I don't know why it's like this. It looks like in 32-bit, I think it's called CDecal, everything just got passed on the stack, kind of like our calling convention, which to me seems nice and simple. I guess there's something better about this because they decided to change to this when they went to 64-bit. Again, ignore floating point numbers just like we did with returns. We don't support floats yet anyway. But let's, in generation, I'm just going to add a global. That's like extern param registers. And that's a string slice. Oh, does it go here? I don't know. I don't know if I've got those brackets in the right place. Yeah, it seems happy. So we're just going to say di si dx, because this is how we sort of have our parameters. Those are numbered. I don't know if that's going to work. Let's see. So we'll go back to our call, right? Go back here. And we want to say like something like this for all of the parameters. We don't want to allocate, but we'll generate an expression, right, to evaluate the parameter. And then where we're going to put it is a register, and the size is going to be, maybe I deleted too much, the param byte size. So if we try to pass a parameter that doesn't fit in a register, it's just going to fail at the moment. If we tried to pass like a struct or something, but that's okay. So extern param registers, and I'm going to put like a param index here. So we can use that here. So that should give us the correct register, although I'm worried about this. I don't think these are going to evaluate to the correct thing. Let's see what happens. We got a window. This is our GLFW window with the title Bangalang. It's not responding, which is fine. That's because in GLFW we should be doing like a loop where we poll for input events, and we're not doing that. So the operating system thinks that it's just not responding. But we've got it working. But I want to know about this. Okay, it seems to be using R8. Oh, I don't know. I mean, these look fine. and then EDI, ESI, then RDX is the next one. Is that right? Yeah, DX. So that should have the title, which I'm pretty sure it does. You know, it has C string 0. And obviously the title worked. So that's RDX. Then RCX takes the top of the stack, which at this point should be this null pointer, right? And puts it in R8. No, it puts it in RCX, but this one puts it in R8. So it did evaluate to the right register, and then we align, and then we call. So it did put it in the correct register R8. I just want to sort of dig into that a bit more, if I may, because what did we call here? We called this register procedure, which takes this one, and if this evaluates to 8 or 9, see, because this is why I'm a bit unsure, because normally we would use register numbered, where we pass an int in, and that should handle the numbered registers properly, but it's going into register named. And I think we're just lucky that in this case it works because it's an 8-byte register. But if it was not an 8-byte register, it would be incorrect. Like if it was a 4-bit register, it would just prefix with E, whereas what needs to happen is it needs to prefix with R and suffix with D. So yeah, so I think we got lucky and that's not correct. What to do about that? What's a nice way that we can resolve that? Let's just say registers name, registers numbered, and then I'm just going to put 8 and 9 in there. And then down here, I'm going to say if param index is less than 4, we use the named one. Otherwise, if it's less than 6, we use the numbered one, and we're going to subtract 4 from the index, right? Because we need index 0 and 1, not 4 and 5. And if we go over, then we just have an assertion. Pass by stack not yet supported, because any additional ones would need to be passed by the stack. And calling C. Okay, that still works. All right. Pretty happy with that. We're over an hour. The only other thing that I was thinking would be nice would be to have this. I think that's going to take a bit of extra time though, so maybe we'll leave that for another video. But this is pretty cool, I think. You know, it's some pretty simple code. The only thing that could make it simpler is if we had just like, if we could just do this, you know, that would be great, I think. I kind of want to make, I'm a little bit unsure about the naming, but maybe nil is fine. And nil means any variable where all of the bytes of the variable are 0. So for a pointer, it means that there's 8 bytes of 0. And if there was like an array or something, it would mean that the whole array is all just zeros. So if you did an equality check with a nil, it just means, is this all 0? That's kind of the idea I have. And then you wouldn't need to even declare this. But I think that's pretty good. I'm pretty happy that we managed to call C. And we got something kind of useful. I mean, it's an empty window. But I'm going to have a bit of a think about it. And let's see what we need to do in order to render some stuff here with OpenGL. Let's just try and render a triangle. See what's required for that. Maybe we need some extra language features to get that working. I think that's more interesting, right? You know, if we have some interesting goals, instead of just like, let's add this feature to the language, let's change this part of the language without really having anything to do with it, like anything real interesting. Okay, I think that's enough for today. Thanks for stopping by. Have a good one, and I'll see you later. Ciao for now.